Hello and welcome to Unsupervised Thinking, a podcast on neuroscience, artificial intelligence, and science more broadly. We are a group of computational neuroscientists. I'm Grace.
I'm Josh.
And I'm Jan.
Friend of the show, Jan, is back again. And the topic for this episode is reinforcement learning, which is a really big topic, and we'll see how we get through it. So what we read to talk about reinforcement learning is a paper called Reinforcement Learning with Marr, and that's by Yelnev and Angela Langdon, and that's from 2016. And then we also read Reinforcement Learning, Computational Theory, and Biological Mechanisms by Kenji Doya from 2007. And I want to point out at the top that the first sentence of that paper is, "What is the goal of our life?" So that's the stakes that are involved in reinforcement learning.
That is a difficult question to answer. That's
Well,
the second sentence.
Yes, exactly. So that's the kind of results you should expect. I also came across a different review that you guys didn't read because I found it after I sent the two to you. And that's by Paul Glimcher. And I'll link to that on the website too because it was quite a nice one that I skimmed. So this is like a really big topic kind of in computational neuroscience, just because it like is a really beautiful example of connecting kind of biology and computation and computer science and engineering with neuroscience experiments. And I mean, a lot of that really came together in the last 20 years or so, but this first paper that I mentioned, this reinforcement learning with Marr, that's referring to Marr's 3 levels of analysis. Is that what they're levels of? Is that right? Anyone know?
I think so.
Something like that, like a computational framework, right?
Okay. But yeah, so those levels are the computational level, which is kind of what is the goal of maybe a brain area or something like that. And then the algorithmic level is what are the steps that you would take to achieve that goal, so what are like the rules that you would follow, what's the algorithm that you would use. And then implementation is usually thought of as the actual physical implementation of that. So how do, say, neurons implement that algorithm? Where can you find that in the brain, and can you see it?
And you could also like have a synthetic system that implements it in a different way in most of these settings where people talk about 3 levels, right? So like the implementation level could be any plausible implementation that's sort of hardware or software specific for building out the algorithm.
You can also have different algorithms as well to do the computational.
Yeah, so that's also worth pointing out. So like the computational problem, I guess, is probably unambiguously one thing. Like, no?
Is it?
I mean, in the 3 levels, it would seem like the computational, like the highest level is always like, there's one clear thing. It's like, what is the computational problem you're trying to solve?
Yeah, okay.
You could have different algorithms, and then each of the algorithms could be implemented in a variety of different ways.
Okay.
Right. So the fact that you can, implement things different ways and all of that, that's why it's a nice framework for comparing, say, computers to the brain or something like that. And so that comes up with reinforcement learning because it's considered a good example of this concept. We have kind of things to say about reinforcement learning on all of these levels, which is kind of rare. I mean, people obviously try to analyze a lot of systems according to these levels and brain areas according to these levels, but you can't always make clear statements about them that really span a bunch of different fields. But with reinforcement learning, it seems like you mostly can now. So that's why it's kind of important as a thing to look at as a success of something. I don't want to say it's a success of computational neuroscience because it's like a lot of different fields are the reason that we have the answers to the different levels, but it's come together under this kind of computational neuroscience framework.
Yeah, I mean, I guess it's rare in science for there to be examples. I mean, there are obviously many examples where this is true, but where you kind of have comprehensive understanding of the problem from like many different perspectives at many different levels of abstraction and analysis. And in sort of neuroscience, Marr's levels are one example where things could span these sort of multiple levels, but there are other examples like where you have evolutionary explanations and genetic explanations and behavioral explanations or things like this. So like Marr's levels for computational neuroscientists, perhaps for some computational neuroscientists, represent the sort of dominant three levels where like you'd be happy with your understanding of a system or a process if you understand it at all three levels. But for other parts of science, there are other sort of levels of abstraction where you have sort of this multi-level system and you want to explain it at all the levels, and that maybe you fully understand something if you can explain it at any of those levels.
Yeah, and another cool thing about it is that the concepts that we'll talk about that kind of make up reinforcement learning were things that were being developed in parallel in different fields. So like engineering fields were thinking about how to solve certain problems, and they came to solutions that look like reinforcement learning. And psychologists were studying how do animals respond to different things in their environment, and how do they learn by getting feedback, and that kind of resulted in finding these rules that look like reinforcement learning. And then after those things were kind of stitched together, there were experiments that looked at, is this happening in the brain in the way that we think it is? And so it was kind of a beautiful story in that sense too. And so we'll talk about, we're kind of going to go through these three levels and talk about reinforcement learning at each of them. But first, we should just kind of define some of the basic terms that we'll probably end up using, because we don't want to use them without defining them, but they come up very naturally in these conversations. So the definition for reinforcement learning that comes up in the Kenji Doya paper is that it is a framework for an active agent to learn behaviors on the basis of a scalar reward signal. So does anyone want to parse that?
So, right, the setting is basically that you have what is referred to as an agent, and they're interacting with what is referred to as the environment. And the agent observes something about the environment, like something like the state. And the state may consist of information about like where it's located, or like what its configuration is. So like, if it's a body, like if it's standing or sitting, or more precisely, what is like the sort of precise pose of its body, or like if it's a self-driving car, what is the direction of the car, and like where is it located using like GPS and this kind of information. So that's like the state of the world that you observe, but you only observe it sort of partially, usually through noisy observations. And then you take actions in your environment as the agent. So the agent sees what happens in the environment through its observations, has a policy which the policy sort of defines how the agent acts, what actions it takes, what decisions it makes, depending on what observations it sees or what state the world is in. And then the agent's actions will influence the environment. And so sort of you can think of it kind of just in turns, where like the agent takes an action, this affects the environment, and then the environment changes are perceived by the agent, which then takes more actions. And obviously this is happening kind of all constantly, but you might represent it as like the agent acts, the environment is affected, and then the agent observes, and then the agent acts.
And then the kind of second part of that definition talks about the learning on the basis of a scalar reward signal. And the relevant bit there is the idea of it being scalar is that it's kind of just a single value that can be, positive or negative. It can be high or low, but it's not the feedback that you're getting from the environment after you take these actions is not very detailed. It's just kind of good or bad, or, very good, very bad. That's the kind of feedback that you're getting from the environment, which is in contrast to different kinds of learning that come up in machine learning or even in neuroscience, which would be supervised learning or unsupervised learning. Those kind of form the three major learning categories. And in supervised learning, you get a much more detailed feedback of kind of what you did wrong so that you can update yourself and learn through more detailed feedback. Unsupervised learning, you don't get any feedback, and you just kind of see if you can find any patterns in the environment you're experiencing or the data that you have. So reinforcement learning kind of falls in between those two because it's this medium amount of feedback that lets you know if you're kind of on the right track, but it doesn't give you very detailed information about what you've done right or wrong.
And in practice, the reward is, it depends on the environment, right? So if you're thinking of a mouse running through a maze, the reward can be a bit of cheese at the end of the maze. But it can also be, for humans, a lot of the studies, they actually just use money as a reward in some of their experiments. And I guess for robots, it would be, the sort of, the user defines completion of a task successfully as a reward of +1 generally or something like this.
Yeah, and so I want to go back to this idea of the agent acting and it impacts the environment and then responding to that environment, and this kind of endless loop that is present in reinforcement learning, because I think that also makes it pretty unique. I feel like in a lot of neuroscience experiments, especially, things are kind of trial based, and it's very just like you're presented with an input and you give an output, and then that's the end, and like the world resets. And having this loop where you keep changing the environment, which means that you're kind of changing the world that you see, the input that you get, it can really like make a big difference in the whole learning procedure and how difficult it is. So that's something that I think is interesting about reinforcement learning, and like a really serious and important complexity that doesn't come up in too many other topics, except sometimes in sensory processing, like the actions that you choose to make to sense your environment. People will study that, and what choices can you make to like best sense what's around you. But it's just a type of complexity that's lacking in a lot of neuroscience studies.
So yeah, I mean, you can more generally this is differentiating relative to other forms of like machine learning or statistics, in that it is like this closed loop setting, basically, where what you do, or in the case of a model, what your model does at a given moment affects like what it sees later. So like in statistics, a common assumption that people will make when they're doing like fitting models to data is that the data is generated by like an independent and identically distributed process. So like when you see data that streams in, the data comes from some distribution, and you can estimate things about that distribution. But what's different about RL, and like framed this way, is that like at every moment when you make actions that change your environment, you're changing the distribution of data that you're seeing.
But your description of like this closed loop thing also would apply to like non-reinforcement learning thing. Like, if you have supervised learning, if you give a non-scalar feedback a system that does that, you can also change your actions dependent on that, right?
So adaptive algorithms like can occur both in the RL setting and like in the supervised learning setting. So if you think like I have a model, and that model is updating over time based on the sort of stationary data that it's receiving, or data from the same distribution over time that it's receiving, and the model gets better, then it is changing, but it's changing in a way that is like only getting better, and where the actions don't really affect the environment. The assumption there is it's sort of like in the conventional supervised learning case, the model isn't affecting the data that generates it. The model isn't producing actions. The model is just sort of like a passive observer of the world, allowing you to like predict on the sidelines, kind of.
Yeah.
In the RL case, because you're using it to take actions, as the model that decides how to act based on what it sees gets incrementally better or different, even if it's not better, it changes the kinds of data that it produces for itself via its interactions with the environment.
And so, yeah, basically this kind of recurrence, anytime you have recurrence, you can like kind of go crazy, which is the problem. Like you could make a bad action that puts you in a bad place that makes you make another bad action. And so that's why it's like a particularly challenging problem, because you basically need to be thinking a few steps ahead, so to speak. And maybe that's a good way to talk about the last term we should probably define, which would be value. So value is usually defined in terms of like a state. You're in your environment, you sense kind of what's going on, and that state has a certain value associated with it. And that is usually defined as the amount of reward you expect to get in that state plus some function of the reward you expect to get in the future, but that's kind of discounted so that you don't care as much about future rewards. You care about things that are more closer in time to you, but you care a little bit about the future because you have to care about the future so that you're doing this kind of thinking ahead kind of thing. So basically what this comes up a lot in that you'll think about the value of a state in terms of both the immediate reward that you get from it and also the rewards you could potentially get in the future starting from that state.
When thinking about how to interpret value in the simplest way, it's basically just each state is going to have an amount of an expected reward you would see if you behaved according to a particular policy from that state forward. So the value of a state is intrinsically dependent on what kind of policy you have. So for two different policies, a state has different value.
Policies can be, I mean, they can be anything, right? It can be even just like roll a dice and move in the direction that your dice tells you if it was a four-sided die somehow. Or maybe if it's like there's 6 directions, I guess. Yeah, but I mean, so it moves up from there up to like very fancy things where you like do some sort of, I can't think of a fancy example, something fancy.
Yeah, so like to say like, oh, the value of the state depends on the policy, that seems very complex, but I think it makes a lot of intuitive sense. Like if someone plopped me down in front of a chessboard that was like half played, and, you know, it was technically a few moves away from me winning, I, an idiot, wouldn't know what to do. And so for me, the value of that state isn't particularly high because my policy would kind of be like rolling the dice. Whereas someone who's really good at chess would look at that and they would, you know, have a high value associated with that state because they would know that if they followed the policy that they have in their mind, you know, they could be winning very shortly. Right, so with the baseline definitions down, we can kind of get into the 3 levels. So the first one was computational. And in some ways it feels almost trivial to say that like the computational level analysis of reinforcement learning is just that you want to maximize reward. But that is kind of the basic premise of reinforcement learning. You're trying to learn how to make decisions in the world that get you a bunch of reward. And that can be difficult to do, but it is kind of a simple premise.
So there's other parts that you could think of maybe as being like at the computational level. Insofar as there are some pretty clear abstractions, like that there is a policy and maybe there's a function that maps what the state is to its value. So this is called the value function. This is just how you evaluate states for how much value they have. You might think of these kind of basic abstractions, not any algorithms that use them, but just the sort of very basic abstractions, I think, could legitimately be considered part of the computational level. Like the problem specification includes that there will be an agent with a policy and maybe there's a value function as a useful abstraction. So as of yet, we haven't said like what you would do with any of these things, but just sort of these basic parts.
And one other interesting thing from this paper as well is that there are other, as well as maximizing your reward as a sort of computational goal, you can also have to learn a representation of the task at hand, which I'm not sure, I mean, I guess gets into model-based kind of stuff, but basically like maybe sort of exploration versus exploitation is also possibly, is that a computational level as well?
Yeah, so the paper about Marr's levels talks about this idea of exploitation versus exploration. It kind of the idea is basically like, would you, if you found something in your environment that gives you reward, if you're a rat and there's a lever and you press it and you get food or something, would you just keep doing that over and over because you found something that gave you reward? Or would you occasionally go and explore different corners of the cage that you're in just to see what's up over there? And you could think like, oh, well, you know, if you're just trying to maximize reward, you would just stay next to that lever the whole time. So to understand why, I mean, and we know it's not the case. I mean, animals do explore, humans explore, even when they know that they can get reward from somewhere. To understand why that exploration would happen, they kind of talk about this idea that you can think of curiosity or information gathering as rewarding. And so they talk about these as internal rewards versus external rewards. And obviously that's a little bit harder to study because you can't control it as well, but it is like a premise that they put forth that that's part of the reward that you're maximizing.
So, and a broader point is of course that like what the reward is in the first place, as Jan kind of got at. Like if it's an engineering setting, you just define what the reward is. But for biological systems, there's obviously no such thing as like reward as an like abstract concept. There's like things in the environment sort of provide reward, or things inside of the animal themselves provide reward. So like if the animal is experiencing something new, maybe somehow there's some part of the nervous system which first of all recognizes that they're in a new experience, and then secondarily tells other parts of the nervous system this is kind of like a reward. Or similarly, even if you get food, like let's say you're consuming sugar, it's not like sugar is magically a reward. Presumably, nervous system is evolved to recognize that sugar is like generally a pretty good thing to consume in like evolutionary settings. And so animals have some part of the nervous system that recognizes I'm eating sugar, and then a different part of the nervous system says something like receiving sugar is like a reward. It might not even be so cut and dry as like these are all somewhat like interchangeable currency, right? It's not like novelty and sugar are the exact same thing. So there's obviously like a whole candidate slew of kind of mechanisms for how these different things would be like still segregated channels. Like obviously novelty is different than sugar. They're both rewarding kind of in some sense, but it's presumably the brain reflects this in like a somewhat differentiated way, though this is not totally clear yet. And then when like learning from reward signals, maybe there are somewhere these signals get kind of merged, but they're obviously like to some extent distinct and should be kept separate.
But yeah, the other thing that you brought up, Jan, was the idea that learning representation could be rewarding. And I think that's really interesting and very difficult, obviously. Like if you're, I mean, it's hard to like really think of like an intuitive example, but it's kind of like if you're playing a video game that you've never played before, you don't even know kind of what things on the screen are super relevant to interact with, or, you know, what's just like background decoration or something like that. You need to learn what parts of the world are even kind of options to interact with and relevant things to measure about your state. And to do that just by getting reward feedback is like seems like a very complex problem, and it's not quite as easy as just saying like, oh yeah, information is rewarding and building a good representation is rewarding, because what's a good representation depends on what the task is, and you only know that based on the reward feedback that you're getting. So it's like you need the external reward to know if you're doing a good job on this like internal sub goal. So that's a big thing that people care about.
But I think some of this gets at partly the notion that some of this has to be innate, right? Like you don't learn from reward that sugar is rewarding, right? Sugar is just rewarding. And that's because animals that consume sugar have evolved to like have signals in their body which say this is rewarding.
Yeah, so I mean, this is, I guess you got at something which I thought when I was reading this, which I just realized that I'm not aware of any links between reinforcement learning and evolutionary algorithms and this kind of stuff, but it seems like there is a fuzzy sort of boundary between those two things. I mean, you know, survival is in some sense a reward. Does it make sense to frame it that way?
And you're talking about like the computational use of evolutionary algorithms, you would simulate some kind of simple type of evolution to see kind of what works well in a computer simulation.
So yeah, it turns out that basically there's an unclear boundary for certain algorithms between these. And in some cases there are researchers who work on both, and this is now a relatively common area of overlapping interest.
Right.
More broadly, right, all of these, and I mean, this is not to be too general as to like be saying nothing, but like these are all optimization like schemes, right? You can think about this as you're trying to find a policy which optimizes reward. You could do that by kind of any method that produces better policies incrementally, like as it explores in the environment. So that like you could evolve a policy, you could learn a policy, you could learn a policy by reinforcement learning or by other methods. So sort of you could perform any kind of optimization that's feasible, usually because in these settings updating a policy requires getting samples of experience. And what that means, like the policy needs to behave in the environment in order to have signal to know how it should change to improve. And that signal could then be used by something that like you view as learning, like refining the policy via learning, or as updating the policy via evolution. This is kind of semantic when you're talking about it in a computer simulation. It's obviously much more different for biological organisms, where like the experience that one organism gets within the context of its life has to change its behavior.
Right, so that probably sums up most of the stuff about the computational level. I guess the only other thing that I would say is that you could kind of view it as an open research question to try to reverse engineer what a human's reward function is, like trying to incorporate all these complicated things. And then you could argue that if you could figure that out, you could like RL train a computer to be really smart. But you'd have to know the stuff that's baked in as well, as we talked about. So the algorithmic level, we know we want to maximize reward, but then how do you actually do that in these kind of complicated settings that we talked about, where, you know, you might not even know entirely what your environment is like? What are the rules that you can follow so that you can create a policy for yourself where you're going to be, you know, cashing in? So this is the area where kind of different fields started on it and made their own progress, and some things converged. A big thing that comes up in kind of all of these different ways, not all of them, but a lot of the different ways of talking about how you would solve these problems is by calculating a reward prediction error at some point. That's something that comes up in these algorithms.
So the idea here is, right, like in a given state, you have some estimate of what the value should be, right? And so if you're in some state, you have a sense of like, what reward should I get at the next time step if I take a certain action? And then if you take that action in the environment, the one that you thought would yield a certain, you know, reward, you then, after you've taken your action, you see what reward you obtain. And that reward could be higher or lower than you were expecting. You know, and it could be that you have a model, or it could be more habit. This is another distinction that comes up, like whether it's model based or not. It could be you're in a room and you think in the neighboring room there's a cake and that will make me happy. So if I go into the other room, I'll get a cake, and then the cake may or may not be there. And this would be kind of like a model based reasoning for like how you're computing the reward prediction error. Alternatively, it could be more like a habit. People generally kind of think about this as more like an animal style thing, where like, I don't know, the animal doesn't have any sense of what it's doing, but like it keeps pressing the lever because it's learned in a sort of habitual way that it gets food from pressing this lever.
And humans never do anything like that.
Yeah, this is the claim. It's also the case that it's unclear if there's like a totally clear and clear cut distinction between model based and non-model based. But you could imagine at least that like for smoking a cigarette, for example, it's become a habit. Like, you know, when you leave the bar to take a breather in the fresh air, you're going to grab a cigarette. And, you know, people who smoke don't necessarily even do that because they like have learned like a model where like they think, oh, this is going to be very satisfying if I do it. They might just reach for it kind of almost instinctively at that point. I think that's like an okay model, an okay example of sort of this habitual style of learning. And there you would still have a prediction error if, you know, you grab the cigarette, maybe it's more or less rewarding. And so either this model-based case or this non-model-based case, you could still have these kind of prediction errors.
Yeah, I want to talk a little bit more about the distinction between model-based and model-free, because I have sometimes struggled with it. It seems to me like, so the idea, the word model here that we're saying is just like you have in your mind an idea of how the world works. And so you can actually think through, like, if I do this action, this will be the way that the world changes, and then maybe I could do this other action, and then I'll get this thing, and you could just, like, enumerate the steps because you can predict what will happen in response to your actions. Model free being this, you know, you're not doing that. Even if you could, maybe you're not doing that. It's just you see X and you do Y. To me, it just seems like maybe model free is just like a really simple model of the world.
Yeah. That's what I guess kind of where I stumbled as well in this distinction is because like model free, you still have to know what the reward is going to be given your next action, and that is enough to solve some rudimentary tasks. Well, not beyond rudimentary, I guess, as well.
I agree. I think even viewing this as a distinction is only useful for certain like extremes, right? Like it's clear that it's model based if you're really kind of concretely imagining yourself taking like a sequence of actions or something like this. In a programmed case, like if you're dealing with like robots or AI systems or something, then it's like very clear if you're using the model to like do sort of mental exploration of what could happen and then decide in your current step what you're going to do based on those sort of simulated possibilities.
If you really have kind of like no model of the world, you can still use these algorithms that have reward prediction error, and you kind of use this error signal that you get when the reward you expected isn't the reward that you get, and you use that to update your value that you associate with a given state. And then the values that you have associated with states determine your policy. So that's how you end up changing how you act in response to getting new reward information. And you can do that in this model free way. Other algorithms that can be used for RL kind of do depend on having a model of the world. So if you're doing like a search algorithm where you, like in computer science, there's like tree searches where you kind of enumerate every option you could take from every state, and then every option you could take from those next set of states, and so on to some kind of depth in this tree that you're kind of expanding out. And if you just kind of went down that and found the path of actions that led to the best possible reward, to be able to draw out that tree, you kind of have to have a sense of what actions will be available from the next state and how the environment will change in response to your actions. So that's a difference. It's a kind of a different algorithm that you would use that requires that you have some understanding of how things change. The other thing that we should talk about is how observable is your environment. So in the real world, you frequently can't know everything about the state that you're in because because like sensory organs are not perfect, so you might incorrectly see something, you think there's something there when it's not. Also, if you're in an environment that includes another person, you can't know everything about like what their thinking is or what their next step will be or something like that. So that complicates your ability to predict what'll happen, and it complicates your ability to learn a good policy, because if you can't know everything about the state you're in, then it's hard to decide what action to take next. So that's like a super relevant thing that for a long time, I guess, like people would study RL in, computer science settings where things were fully observable, to just kind of avoid this problem. But it's like a huge problem. So I guess things like games, like chess, are considered fully observable, even though there's someone else there, but you both have this shared information. You know everything that they know, basically.
And it's more than that in the sense that with chess, you could make the best decision hypothetically, like you can make the best decision just by the game state. There's nothing in the other person's head that's going to like magically affect the state of the game. So like the game state is certainly fully observed. The simplest examples I can think of partial observability would be like your visual field, like your perspective as a first person perspective. Like you look out into the world and you don't know what's behind you. You could spin around in circles to get like a better view of the world, but you still wouldn't know what's in like the neighboring room that you can't see.
I like that as a policy. Like every room you walk into, you spin around in circles for a few times just so that like you got it all, and then now your RL becomes really easy.
But of course, if your memory's good, right, then you don't even need to spin around a few times. You could just spin around once.
Yeah, and then the other thing that they talk about is hierarchical algorithms, and that feels like that's something that kind of comes out of intuition. Like, well, when I do something, I break it down into sub-goals. So, like, when I make a sandwich, I go sliced tomato, but I also slice tomato when I'm making pasta sauce or something like that. So you have these sub-goals that are reusable across different tasks, and then your job is to just kind of figure out how to put them together.
But I think I slice tomatoes differently in those two settings.
Okay, it was, like, off the top of my head.
Yeah, I dice for tomato sauce. So.
You guys are the worst. But so this feels like kind of almost a different problem to solve in a way. I guess it's kind of similar to learning the representation of the world, like learning how to carve up your big goal into little goals that will be useful.
Also, I mean, probably easy to think of how to implement that computationally in an algorithm, but like biologically that would involve combining, somehow getting the reward signal to be spread across like whatever, optimally like to the system that like does the small goals. Like how the hell is one scalar reward signal going to give the right information to all of these different components? That seems a bit tricky. I guess also tricky algorithmically maybe. Yeah,
I agree, and I feel like a lot of the neuroscience research on RL is just like a simple model-free setting. So yeah, we don't know, obviously. But another takeaway from this section was that the brain probably just uses a combination of a bunch of different algorithms to solve reinforcement learning problems. So we shouldn't expect to find one clean one.
What a surprise.
Okay, so the implementation level. This is the real guts of it. The stuff that neuroscientists are supposed to really care about. So the big thing that happened here in the implementation level happened in the 90s, so not that long ago by science timescales. And this was this experiment that was recording from neurons in the midbrain, dopaminergic neurons, so neurons that release dopamine to other areas of the brain. And from my understanding, it's to like a lot of the areas of the brain, right? These dopaminergic neurons just like squirt out everywhere.
Yeah.
Yeah. We're all in
Roughly.
agreement on that.
Yeah.
Or at least, a lot of places. This was Wolfram Schultz, is the first author on this paper, recording from these neurons when the animal was performing this task where I think it was like they saw a light, and then later on they received juice, like just squirted into their mouth, and they're water deprived, so this is like super great reward for them. I think in the Kenji Doya paper it said like they received liquid reward, and I just thought that was a funny way to put it. It seems like a name of a hipster beer or something. Right, so they saw in these neurons that at the start of this experiment, when this was like a new setup for these animals, the neurons didn't care about when the light on the screen came on, but when the juice was squirted into their mouth, these neurons were firing. And then over the course of the experiment, they started not firing so much when the juice was squirted in, but did start to fire when the light would turn on. And so it was this switch from these neurons responding to the juice, to the reward itself, to responding to the light, which was an indicator of the fact that the reward was about to come. And so this was a really big deal because previous theory about how you could implement reinforcement learning could predict that that's how you would expect the neurons to respond. This is what you would expect if this system is doing this kind of temporal difference learning, where you're using reward prediction error to update your expected value.
I mean, this is basically the same story as like Pavlov's dog, in the sense that the neurons firing, the neurons firing are kind of like the salivation. So in the Pavlov's dog situation, right, you've got a dog that if you give it food, it salivates as it's eating it and it's happy, it's getting food. And if in that case, it's a bell, and the bell starts to be associated sort of behaviorally and perceptually. And so the dog will salivate when it hears the bell, anticipating that food is going to come. And this is like the neural version of that story, right? The light signals that the reward is going to come at some future time nearby, and the neurons now respond to the light, like the salivation responded to the bell. And so the neurons no longer primarily respond to the reward because they're sort of anticipatory, because that's when the prediction error occurs, right? Like you're going about your life and nothing's going on. Like you're going about your life, and then suddenly you see a light, and like already that's the thing that is now the thing that's discrepant. That's the thing that if you wanted to learn how to make that light happen, that's what you would want to do, because the light reliably predicts the food or juice in this case. And so if you want to learn now in the future learning should like be higher order. It should be like, now I want to learn how to make the light happen. I don't care about making the food arrive. I know the food reliably comes after the light. I want to learn how to make the light happen. And so that's the thing that the neurons are sort of expressing the prediction error for.
And then there's the important follow-up to that experiment as well, right? Which is what happens if you show the light and then don't give the reward. And what maybe is the coolest part of the experiment is then that there's a dip in the firing then if there's no reward present. So you get like this, increase in dopamine when the light comes, and then so that's a reward prediction, as Josh said, because you weren't expecting light to come on, and then it comes on, but then when there's no food after your expected waiting time, there's another reward prediction error, which is a negative prediction error, because you're expecting the food and it doesn't arrive, and so you get this decrease in response in the dopamine neurons. And
like conceptually, what that's reflecting is the fact that now the light is like less good of a predictor for the food, like the consequent food, which initially it was a very good predictor, but now you're saying, I'm not so sure if the light reliably predicts. That's what you're learning from that dip.
Yeah, and think this was maybe in the third review that you guys didn't see, but I'll tell you about it. It said that the amount that the neurons can dip in that setting where you're expecting a reward and you don't get one, they can't dip very much because their baseline firing isn't very high. So it seems like, missing out on a reward isn't that big of a deal because the neurons don't respond that much. There's a limit to how strongly they can respond to that. But then behaviorally, it's known that there's a big, behavior updates a lot when you miss out on a reward that you thought you were going to get. So the question is, how can behavior be updated so much when the neural signal that seemingly supports that learning process is not very large compared to what it is when you get a reward? So it's possible that there are other systems involved in that, or that this small change in the dopaminergic neurons could actually still have a big effect on the learning.
Yeah, I mean, one thing that I would sort of, not really quibble, but elaborate with this point is, this has always felt a little bit arbitrary to me in many cases in neuroscience, right? Like the neural response, it could be, the neuron can fire, right? And if you're assuming that the firing rate indicates the magnitude of something, like the intensity of the stimulus or the intensity of the reward or something like this, the mapping from how many spikes happen per second to whatever the sort of scale is could be kind of arbitrary too, right? It could be the case that 0 to 1 spike per second is a big difference, but then the difference of 1 to 2 spikes per second is a very little difference. It depends on what the readout neurons are downstream. So the sort of scale could be arbitrary. So the fact that the firing rate of one of these neurons only dips a little bit in response to a lack of a reward following a predictor could I mean, we don't know what that it means. Whatever it means to the downstream neurons, which apparently, given the behavioral consequence, just is a lot. So we shouldn't take the absolute scale of the number of spikes per second to mean anything special or privileged, I think, right?
Yeah, but it is in comparison to the spikes per second when you get a reward. So the firing will go up by 30 or 40 spikes per second when you get a reward, and it'll go down by 3 when you don't. But you don't know what that down by 3 means necessarily.
Right? If it's a logarithmic scale in terms of the response to that, then this is, it would be the difference between no spikes and 10 spikes could be very different than 10 spikes and 20 spikes.
Mm-hmm.
Right, so this is kind of half the story. If we know that there's something in the brain that signals when there was a reward prediction error, the second bit of that is that you actually have to update something about the brain in response to that error so that you're actually learning and not just kind of noting that errors have happened. And so the area that people focus on for that is the basal ganglia, which is a collection of cellular clumps in the forebrain nuclei. And so the part in there that's the sub-focus of this would be the striatum, because it receives these dopaminergic inputs. And the idea is that there's kind of special learning rules at the synapses that connect the striatum with areas in the cortex. And so the idea is that when dopamine is there and there's kind of activity happening at the synapse, then the strength of the synapses will go up. But if there's activity at those synapses and there's no dopamine there, the strength might actually go down. So the learning in this area depends on the presence of dopamine.
And so this is called, three-factor learning rule, right?
Yes.
So this is different to most areas of the brain, which, maybe not most areas, maybe most areas that are studied in the context of maybe synaptic plasticity, which is usually cortex, I guess, where it is mostly thought of as a two-factor learning rule, where it's pre and post is the classic kind of Hebbian learning rule. And so this dopamine plasticity adds this third factor, which is the presence of dopamine. It's pretty cool because it was predicted it's a very simple sort of mathematical framework for learning that basically said, if you have these three factors and you update your synaptic weight based on this, and you have this reward prediction error, then this is what we expect to happen. And it's found in there are neurons that do this. It's kind of crazy when you think about it that way.
Yeah, that's why it's the poster child for Marr's levels of computational analysis. But there are obviously other things that don't fit in neatly with this interpretation of neural activity. I think one of the things is that dopamine is just associated with a bunch of other stuff too, and I mean that doesn't mean it's not doing reward prediction, but it's got other roles as well, so that just complicates how the system could work if it's got multiple jobs to do. Oh, they also don't know how the reward prediction error is calculated, I believe. Whether it's calculated like amongst the dopaminergic cells or if it's inherited from some other area that does the calculation and just tells them when to fire. But that's obviously an important question.
Mm-hmm. Yeah, I mean, it almost feels like the way it's studied first is just to observe that there is a prediction error. And like in reinforcement learning algorithms, right, you have a value function that you're learning that's supposed to be able to compute the value of a state. And that's like potentially a very complicated function. It says like in any state that I could be in any, for chess, any board state of the game, or when you're trying to do other things, like what the state of the world is that you observe, or at least insofar as you observe it, what is my expected reward into the future? In the neuroscience setting, it's almost like magic. It's just the brain produces the reward prediction error, and clearly this is very complicated. And people do. I don't mean to over simplify. People obviously study different areas of the brain that sort of represent or predict the sort of value or consequences of a given state. So it's not like crazy. I mean, people already do study where value, where the brain represents the value of given states. But then the idea that you get this dopamine signal that sort of spreads this around, it's a very complicated mechanism by which the reward prediction error is computed, and then it has to be communicated to the dopaminergic system, which then has to distribute it to everywhere else, or something like this, right?
Yeah.
Yeah, and the other mystery that was pointed to was, so the basal ganglia, before any of this dopamine reinforcement learning stuff, it was known that the basal ganglia is involved in action selection and action execution. And it has these two separate pathways that are the direct and indirect pathways, or the go and no-go pathways. And I guess it's just not quite clear actually how those fit into this system. It could be part of the algorithm that is not yet understood. But that's another kind of outstanding issue which you would want to connect, obviously, because these seem to be involved in this process of action selection. So then overall, the kind of thinking, going back to the three different types of learning that we spoke of at the beginning of the episode. So people say that reinforcement learning is happening in the basal ganglia, and supervised learning is done in the cerebellum, which is a brain area that we want to have an episode on soon. And then unsupervised learning, they say, happens in the cortex, the cerebral cortex. So this is kind of, if you wanted to chunk the brain up and associate each area with different learning algorithms, that's how you would do it.
That seems a bit, like maybe broad strokes. Clear.
Maybe broad strokes.
Was it did they discuss in the Glimcher review about what Josh was talking about with where the reward is actually calculated? So I mean, there is imaging studies done in some parts of the prefrontal cortex. So I think they identified one area which seemed to be about the magnitude of reward, another area which seemed to be about the uncertainty of the reward. I don't have the areas to hand.
Some of this has to do with orbital frontal cortex.
Right, okay. Yeah.
But I don't know exactly the full story.
Yeah, I can't say. Yeah, but so, I mean, there are imaging studies that look at these things, and they use humans. Do they do it with economics, with neuroeconomics?
Oh, yeah. Well, I mean, that certainly sounds like something they would do.
Yeah.
So yes, probably. I think
cool.
People who don't call themselves neuroeconomists also do that. Yeah, that's another thing about reinforcement learning, is how interdisciplinary it is. It's like psychology and computer science and engineering and neuroscience and economics.
And psychiatry.
Yeah.
I think that's probably like one of the more interesting sort of ways of applying this theory is in sort of addiction or sort of these sort of OCD orders as possibly some kind of breakdown in the way in which the reward is predicted or acted upon in the brain, I guess. I haven't read too much about it, but
yeah, but I mean, you could even, like, certain things seem like, for example, consider something like the duration of time that you wash your hands. With an OCD person, it's presumably habitual, like they're washing their hands for 20 minutes or something like this, and maybe they're continually getting reward due to some broken down system when they do wash their hands. So this could be about what actions you select, like how frequently you decide you're going to consume a drug, or it could be about something that distorts the properties of that action. If you think about like washing your hands as one action, it's like extended.
So the last major kind of application of these ideas is in actually solving real problems in a computer science or engineering sense. So another thing that makes reinforcement learning cool is that it's recently been used to successfully play video games, to have a system learn how to play video games. Atari was the system that was used, and it was just at a level of performance that exceeded humans for many of the games. And so this is kind of a major advance that was due to reinforcement learning, which moves it beyond kind of this, fun theoretical exercise to think about how these systems could work and look at them in really simplified neuroscience settings. If you can actually apply them in complex settings and get real results, that kind of, it says something about being on the right track about these algorithms, and also just like it demonstrates their power.
Yeah, and actually I think it was last week or a couple of weeks ago, I saw a paper published where they got did you hear about this? A glider to, like an actual physical glider, using a pretty simple reinforcement learning, I think.
Like an airplane, like a toy?
Well,
airplane?
like one of those, like, I guess it was maybe 2 or 3 meters wingspan. So like a drone type thing. But they trained it to basically learn how to catch and soar on thermal winds. So like in the real world, in the field. So that's kind of like, and it learned this in, I think, maybe 2 or 3 days of training. So this is like, a lot of the criticisms of maybe the Atari style things is that you needed like thousands or millions of hours of training or whatever it was. With this, it's a physical object that's in the wild, so you can only train in real time, and it did it in a few days, rather. And it was a pretty simple sort of setup, I think, but it's quite cool.
Yeah, that's pretty cool. Did it not like break a bunch of times as it was learning?
I was looking for videos. I couldn't see any videos. Do you know much about this, Josh?
So I don't know too much about this,
okay.
But I mean, my sense would be for something where it like a flying example, especially if they start it in like a good place. So like a lot historically, robotics is. I mean, people have been trying to get robotics to work well using reinforcement learning for a long time, and often what they'll do is they'll sort of initialize the policy somewhere, semi-manually specified. That's like broadly sensible, maybe not like great, but like broadly sensible, and then you can often relatively quickly get reinforcement learning to work. So maybe you could imagine a setup for the glider where maybe it's got a failsafe. A lot of these real world settings are predicated on like being able to design a partial solution that's not good and isn't exactly what you want, but that sort of saves you from failing extremely or something like this, or resetting you automatically to a position where then you could try the learning algorithm again.
Cool. Anything we forgot to say about reinforcement learning? A giant topic I'm sure we covered all of.
Nope. I think that's everything. Is it?
I mean, I think we should go back to this Kenji Doya article and read his second sentence.
That's a good bookend. So the first sentence was, "What is our goal in life?" And the second sentence is,
"That is a difficult question to answer. But our life is a chain of actions to satisfy our needs or desires, many of which ultimately lead to our survival as individuals and proliferation as a species." I thought that was kind of a lofty way to start a paper on reinforcement learning. But I guess it gets at, on some level, this sort of tie-in between evolution and RL that Jan was talking about earlier as well.
Yeah.
Just the idea that like kind of the problem that we face even if we don't want to think about it as a problem, but like kind of the setting that life exists within. Maybe not the meaning of life, but like, or what is life about? It's more like the setting that life exists within is just animals do stuff in the world. And sometimes that stuff causes the proliferation of species and sometimes it doesn't. And like both across lifespans and within an individual lifespan, you want your behavior to like, not that you want your behavior to, but like more things that exist now will behave in such a way that their lives are longer, they reproduce, and or their offspring have advantages because the things that didn't behave in that way stopped existing. Roughly.
Okay, a lofty way to start a paper and a lofty way to end a podcast. Till next time. Hey, if you're still listening to this, you must really like us. So how about you go to iTunes or Stitcher and rate the podcast, give us some feedback. You can also go to our website, unsupervisedthinkingpodcast.blogspot.com. You can comment on different episodes, or you could give us ideas for new topics you want to hear about. We would love to hear from you. Thanks.